Okay, Izzy, I hope you're having a good night. Acid-base reactions, otherwise known as neutralization reactions. Uh, Now, first of all, you always have to look at stoichiometry. I know that's a word that people in first year chemistry kind of tend to shy away from. But really what we're looking at is we're looking at the proton from the acid and the hydroxide from the base, and they are going to come together to form a salt. A salt, again, is any ionic compound. It doesn't have to be sodium chloride plus water. So you have to keep that in mind. So if I've got one H here on an acid, I need one OH here. And that makes the stoichiometry perfect. So the H will meet up with the OH to form H2O, and the sodium and the chloride will meet up to form that salt, and that salt is sodium chloride. Now, they're not all going to be one-to-one. This is a one hydrogen, one hydroxide to give 1 mole of water, and of course 1 mole of sodium chloride. So let's take a look at some of these on this sheet here. I see that you have H2SO4, and this is sulfuric acid, and we call this a diprotic acid. Diprotic. And what that means is I've got two protons, two hydrogen ions. And I'm going to react that with magnesium hydroxide. And notice I've got two hydroxides and I've got two protons. And also, if you remember your polyatomic ions, sulfate is a -2 and magnesium is a +2. Magnesium +2, sulfate -2. So that's going to form magnesium sulfate, just a 1-to-1. And I've got two protons, two hydroxides, and so the overall balanced reaction will be H2SO4 plus MgOH2, magnesium hydroxide, and that's going to give magnesium sulfate plus, now I've got two H's and two OH's, so I'm going to have 2H2O. Let's make sure everything adds up. I've got 1, 2, 3, 4 hydrogens. I've got 4 hydrogens, and I've got 2 oxygens, 2 oxygens. So if you see a diprotic acid, and it's reacting with something with 2 hydroxides, then it's just a very simple 1-to-1 ratio. The spectator ions in this case would be magnesium +2 plus sulfate -2. They're just going to be floating around in solution. The hydrogens and the hydroxides, excuse me, formed water. So the net ionic equation, if you have to do that, is going to be 2H plus 2 OH minus to give 2H2O. This is called the net ionic equation. Oh, not that. And the spectator ions are magnesium and sulfate. Okay, let's take a look at the next one. It's letter B on your sheet, and that is HNO3. Now, how many hydrogens are there? There's one. This is called a monoprotic acid, but I'm reacting it with aluminum hydroxide. And look how many hydroxides I have here. I have 3 of them. So I better have 3 hydrogens here. So I have to put a 3 there. And then what I will have on this side of the arrow, I'm going to have 3H2O plus AlNO3, aluminum nitrate. Notice that there's 3 distributes. I get 3 protons, I get 3 nitrates. And aluminum has a +3 charge. So that aluminum is going to grab those 3 nitrates and form this, but that's going to stay in solution. So if you want to write this out as a total ionic equation, you're going to have this. So you're going to have 3 H pluses plus 3 NO3s, 3 nitrates, to give plus an aluminum with a plus 3, plus 3 OHs, and that's going to give, I'll just continue down here on the next line, that's going to give, well, this is going to go with this and form 3 H2Os, and I'm going to get Al plus 3 ions and 3 NO3 ions. They're going to stay in solution because aluminum nitrate is soluble. And if I cancel out my spectator ions, that's that, 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 and that, then we get the net ionic equation 3H plus 3OH minus gives 3H2O. Now, what you need to recognize is my acid monoprotic, diprotic, or triprotic. And that means 1 proton, 2 protons, or 3 protons. And in that case, you're going to have to look at that appropriately. So let's take a look at H3PO4. Hang on, let me turn the page here. Now, look at this. Is this monoprotic? No. Diprotic? No. Triprotic? Yes. 3 hydrogens. And I'm reacting that with calcium hydroxide, right? And look at that. I've got 2 OH groups here. I've got 3 protons here. So somehow we have to balance that by finding the least common multiple of 2 and 3, which is 6. So if I put a 2 here, I'm going to have 6 protons. And if I put a 3 here, I'm going to have 3 hydroxides. So when I go ahead and do this now, I'll continue down here so the camera can get it. I'm going to have, well, 2 times 3 is 6. So I'm going to have 6 protons, and I'm going to have 6 hydroxides. So I'm going to get 6H2O plus. Now, let's take a look here. I'm going to get 3 calcium plus 2s plus 2 phosphates with a minus 2. And these are spectator ions. And you know you're doing okay because take a look over here. 3 times minus 2 is minus 6. I'm sorry, this should be a minus 3. Phosphates are minus 3. 2 times minus 3 is negative 6. So I have a plus 6, negative 6. That cancels out. The charges then are the same on both sides. I don't have any charge on that side, and these charges cancel, so we're good. So the net ionic equation is going to be 6H plus 6OH minus to give 6H2O. And again, you're looking at that common multiple between 3 and 2. Again, you always want to combine hydroxides and hydrogens. So if I've got 3 of these, I better figure out a way to get 3 of those, and or in this case 6 and 6. So you're good on that one, I hope. The next one's pretty straightforward. It's HI, hydrogen iodide or hydroiodic acid, plus KOH. Now take a look. I've got 1 H here and 1 OH. So this is beautiful. I get 1 mole of H2O, plus I get some Ki, potassium iodide. Now this stuff, Ki, is going to stay in solution. These are spectator ions because they're just floating around, not doing anything. But what happens is this proton reacts with this hydroxide to form a mole of H2O. And let's take a look at the last one. The last one says I've got HBr. Now, how many hydrogens do I have? How many protons? I only have 1. I've got 1 there. And I'm reacting to that with barium hydroxide. Now take a look at this. Barium gets a plus 2 charge always. And hydroxide has a minus 1 charge. So I have 2 hydroxides to every 1 barium. So I have to put a 2 over here because I need 2 protons. So again, I'll continue down here. You're going to get 2H2O plus BaBr2, that's going to be dissolved. The barium plus 2 and the two bromides are going to be spectator ions. Okay. And it says, how are the net reactions for each of the examples above similar? Well, the net ionic equation always forms between protons and hydroxides to give water, and they're all similar because the cations that are left, for example, K and I, and the anions, they're just spectator ions. So they're just floating around minding their own business. Now, let's take a look at another one, really. This is not on your sheet, but maybe you could, what I'll do is I'll write one here, and you can go and try it and pause the video. So let me make up one here. I've got HNO2, that's nitrous acid, plus AlOH3. Now, what am I going to get? How do I balance this? So pause the video, you give it a try, and then I'll come back and do it for you. Okay, so this is only one proton, but over here I've got 3 hydroxides, okay? So I better put a 3 here. And again, this is nitrous acid as opposed to nitric acid. So your net equation will be 3H plus 3OH minus, and that gives me the 3H2O. That's the net ionic equation. If I have, maybe I have some hydrofluoric acid, and I want to react that with strontium hydroxide. Okay, well, what am I going to do? There's one H there, 2 OHs there. I put a 2 there, and I give it 2H2O plus SrF2 aqueous. Maybe that's aqueous. I have to check the solubility on that. But anyway, that would be your balanced equation. So again, you need same number of H's as OH minuses. And you're only going to have these options. You're going to have a 1-to-1, one proton to one hydroxide, maybe a 1-to-2, and a 1-to-3. Or you might have a 2-to-1 or a 3-to-1. So for example, if I have something like this, H3PO4 plus NaOH, well, look at this. I've got 3 protons, a triprotic acid. So I need a 3 right there, because phosphate has a -3 charge on it, and you're going to get these product. You're going to get 3H2O plus Na3PO4, and that's aqueous because all sodium salts are aqueous, and there's your balanced equation. So I hope that helps. If you need anything more, let me know.